In this chapter, students will learn multiple methods to solve whole number multiplication problems. Students will move from relying heavily on models to solve multiplication problems towards becoming more fluent by using algorithms. In fourth grade, students began with 1-digit by 2-digit numbers and modeled multiplication equations by using base 10 blocks as well as the box line dot method. For example, let's model 5 times 23. Here it is modeled using base 10 blocks, and here it is using the box line dot method. Students previously learned that area is additive, so 5 times 23 is the same as 5 times 20 plus 5 times 3. 5 times 20 is shown here with the base 10 rods and here with the 10 sticks for an area or product of 10 tens or 100. 5 times 3 is shown here as 15 cubes or 15 dots. The total area is 100 plus 15, which is 115. 5 times 23 is 115. Students then moved on to open arrays to represent 3- and 4-digit factors by a 1-digit factor, and then 2-digit factors by 2-digit factors. For example, let's solve 58 times 45 using an open area model. Start by drawing a square. 58 will be decomposed into 50 and 8, which will be represented along the left side. 45 will be decomposed into 40 and 5, which will be represented across the top. Separate the place values in the model by drawing lines in the area model. This first area represents 50 times 40, which is 2,000. The next area represents 50 times 5, which is 250. The third area is 8 times 40, which is 320. And the last area is 8 times 5, which is 40. Now add all the partial products together for a final answer of 2,610. Let's move on to the concepts and skills taught in this chapter. Students will focus on algorithms and standard algorithms for multiplication. An algorithm is a sequence of steps that, if followed, is guaranteed to reach a goal. A standard algorithm is based on decomposing numbers into base 10 units and then carrying out the single-digit computations with those units. Here is a table of written methods for multiplication in 5th grade, and they are all algorithms. Let's focus on methods 1 and 2. These methods are the preferred standard algorithm for 5th grade because of their strong reinforcement of place value and the properties of multiplication. Methods 1 and 2 show partial products from the area model learned in 4th grade. Let's look back at the area model we created for the multiplication problem of 58 times 45 and correlate it to the algorithm used in method 1. This algorithm starts with the ones place in the second factor, then moves to the tens place, or from right to left. 5 times 8 equals 40. This is shown in green on the bottom corner of the area model and represents the ones place multiplied. The next step will be to multiply 5 times 5 tens, or 50, for a partial product of 250. This is shown in the red part of the area model. The next step will be to move on to the tens place in the second factor, which is 40. 40 times 8 is 320. Then finally, 40 times 50 is 2,000. Now add all the partial products for a final product of 2,610. In the algorithm, the multiplication equations are not written out as they were in 4th grade. Method 2 is also a partial product algorithm, but instead of starting in the ones place with the second factor, start in the tens place or move from left to right. Notice all the same partial products are there, just in a different order. Method 3 shows the partial products written as diagonals and allows the regroup numbers to be written below the line and thus in the correct place, and goes from right to left. Start with the 5 times 8 is 40. The 0 will go in the ones place and the 4 will go in the tens place in a diagonal. Next will be 5 times 5 tens for 25 tens. A 5 will be recorded in front of the 0 in the tens place, and the 2 hundreds will be recorded as a regrouped or carry number in the hundreds place. Then move on to the tens place and multiply out the 40 as seen here. The final product can be found by adding all the digits for a total product of 2,610. Method 4 shows the regroupings with the carries on top, and is the typical way the algorithm was taught in the past. However, it can be difficult for some students for a couple of reasons. First, the carries are placed incorrectly. For example, when recording the partial products for 58 times 45, notice when multiplying 40 times 8, the carried number of 3 is placed above the 5. This makes it seem like it is in the tens place, when in fact the 3 is in the hundreds place. Second, having the carries above disconnects them from the rest of their product, so the steps and the meanings of the digits can get confusing. Third, the process alternates between multiplying and adding, increasing its difficulty. One other method that is not explicitly taught in this curriculum is called lattice. It is similar to multiplying with the area model, but the partial products are written without zeros. The factors are separated by place value, then the first factor is written across the top, and the second factor is written along the side. Next, diagonals are placed to locate the different place values of each partial product. The products are then filled in as seen here. Then the students add each diagonal for the final answer. This method does allow multiplication to be done first and then addition done last. However, there are several drawbacks. First, there is a disconnect in place value understanding. Second, there is a disconnect from the area model and the base 10 blocks, which disrupts the progression students have made from the concrete to abstract. If this method is used, it is important that students label and emphasize the place values for understanding. Students will move from relying heavily on models to solve multiplication problems to becoming more fluent by using algorithms. In this chapter, students will learn multiple methods to solve whole number multiplication problems. While there are a wide variety of methods to multiplying multi-digit numbers, it is important that students are able to explain why the method works in order to avoid confusion and mistakes. It is tempting to simply give an algorithm with a set of rules, but it is imperative to make sure the understanding is there first.